The question still is, which way is it going to go? And so we have 1 vote for right, 1 vote for left.
Why is the electric field going to the left?
All right, first off, I don't know what the configuration is that would create this. This is just hypothetically if it does. All right, it's going to the left because the slope of my potential, at least from the math point of view, the slope of my potential graph is positive, and the electric field is the negative of the slope.
Okay.
Do you have an insight?
I think it's going to the right. It wants to go opposite the electric field.
And that's another way of looking at it. So from the point of view of the electric field's going this way, negative charges in that electric field go the opposite way. So it is going to go that way, as Colin was saying. From the point of view of energy, the change in potential energy, the electric potential energy is equal to Q times the change in electric potential. This is when we first defined it. With a positive charge, when it went to a lower potential, my delta V was negative, Q's positive in that case, and so I had a negative change in potential energy, therefore I had a gain in kinetic energy. For the negative charge, if it kept going off to the left, it's going to go to a lower potential. So my delta V would be negative, Q is negative because it's a negative charge now, which means that ultimately my change in potential energy is positive, it gains potential. It has to go back this way. As a matter of fact, it's going to oscillate back and forth around that point, or around that point. So again, 2 ways of looking at the exact same problem. All right, questions to hear?
So, going back to the electric field graph,
Right.
would it oscillate between the peak and the valley?
Between here and here?
Yeah.
This, I don't remember how I actually worded it. The intent was it was just a small little nudge.
Okay.
So I wasn't putting so much energy into it that it could, overcome another hurdle.
Okay.
So, apologies if I did not word that correctly, or I left it out, but this would correspond to this point right here, where it's, in theory, the steepest. So yeah, the intent definitely was not that I pushed it to the point where it would seek a different minimum.
Okay.
All this is well and good for a one-dimensional problem, and that's and we're really dealing mainly with one-dimensional problems, but what if it's a two-dimensional thing? So let's set that up. Suppose I have a series of equipotential lines defined by V is equal to XY. Let's set up one coordinate system here. So this would be, say, V is equal to 1. And so if this is 2, this would correspond to 1/2. So we have any combination of X and Y such that the product is 1. That's this equipotential line. They all have the same value for V. If I had X is equal to 2, then it's going to look something like this. V is equal to 2. This is a different equipotential line. V is equal to 3, and so on. First off, the electric field. I know that the electric field is perpendicular to the equipotential line. So let's write that, I know it's been written down before. but the electric field is perpendicular to the equipotential line. So along here, it's somewhat perpendicular. Which way is that electric field going to go? Is it going to point outwards or, sorry, away from the origin or towards the origin?
Towards,
Why?
because as the voltage, as the voltage is getting bigger, your electric field is getting more negative. So, makes sense.
As the voltage gets bigger, the electric field is getting more negative.
So they just have they have a negative relationship. As one goes up, the other goes down.
Yeah, as the slope goes up, the other goes down. So, I mean, your voltage can get bigger if it does something like that, but your electric field is getting closer to zero. I guess it still goes the same way. Okay, another reason? It is pointing that way. If I have a positive charge here, I have some point here, call it P1, and some point here, P2. Which has a higher potential, electric potential? Okay, why?
It's closer.
Yeah. Formula from a point charge, KQ over R. So as R gets bigger, my potential gets smaller. So it gets smaller the farther I go away. What about electric fields? Which way is the electric field going at point P1 and P2?
To the right.
Yeah.
Away from the positive charge.
Right. So, for me, it's helpful when I look at this to go, all right, so if I simplify the problem, and then I'll generalize it later. So simplifying it, if I have a point charge here, I know the electric field goes away, and I know the electric potential gets smaller. So that holds true more generally. As my electric potential gets smaller, that's the direction of the electric field. But how do you actually find the direction of the electric field at a specific point? I know it's perpendicular to it. And if I drew it perfectly, potentially I could figure out what the electric field is. But it'd sure be nice if I could do some little bit of calculus.
Yeah.
You have the way?
No.
Oh. I didn't know if, who's in or had Calc 3? All right, so that's, all right, so all of you are in or had, how many have had it already? Okay, that looked like and a half, was that a half there?
I had it. I don't see.
I'm going to introduce to you, or at least from my point of view, if you've had Calc 3, you might have seen it before. The nabla. I got one knot over there, and any recognition from those? We got a couple of those. And Enrique, you're still trying to decide?
Seems familiar, but
I've heard it called a couple other things, but nabla is the one that I first heard. This in physics is known as a vector operator. Actually, probably in math too, a vector operator. It is a vector, so there is a direction to it, but it's called an operator because it doesn't really have a value, it performs an operation. So in rectilinear space, nabla is equal to I hat del x. Those are del's, it's not the number 2. Plus j hat del y plus k hat del z. They're kind of like derivatives, but a little bit different. All right, so partial derivatives. So we've got, some recognition for partial derivatives, got, all right. Now, Devon, I'm guessing you have not dealt with partial derivatives?
Count two?
Is that a Calc 2 thing?
Yeah, that part. I don't know about the Calc three. If you implemented this in Calc three, I wouldn't know about that.
All right. Well, a refresher or introduction. Partial derivatives are very simple in terms of operation. If I did dv dx, where v is equal to xy, that would be equal to y y plus x dy dx. So potentially both of them could be related to x. So you take the derivative of the first one times the second one with respect to x, and then plus the derivative of the second one times the first one, using the product rule. That's straight up derivatives, the Calc 1 stuff. Partial derivatives is you assume that anything that is not the differential in the denominator, in this case, anything that's not x, you assume is a constant. So that's just equal to y.
Okay.
Oh, bad notation there. That should be a del on the bottom. I am making the assumption of traditional x, y, z axes, where I hats in the x direction, j hats in the y direction, k hats in the z direction. There is more generic notation, but it's just not worth it. So if I'm dealing with multiple dimensions here, my electric field is the negative, the NAD law operating on the electric potential, or, and I think this is a Calc 3 thing, gradient, div grad curl. Okay, not coming up with a whole lot of recognition right there. Negative gradient of the potential. Later on, if you run across gradient, you go, yeah, okay, I know that stuff. There is a book that I highly recommend called Div Grad Curl and All That. Probably, if you want a conceptual understanding of what gradient, divergence, and curl are, Div Grad Curl and All That, I would recommend. I have no idea if it's still published or in print, but I found it incredibly helpful. So what we would do in this particular case is, I have only x and y, there's no z parts to it. And so my electric field would be the negative of, we take the negative I hat times the partial with respect to x, minus j hat times the derivative with respect to y. And that's my electric field. Let's see if this makes any sense whatsoever. So if I know that as my equipotential line shoots out farther and farther on the x-axis, my electric field should be closer and closer to pointing downwards. So the larger value of x means the smaller value of y, so this term starts dropping off to 0, and so it almost becomes dominantly the value of x in the negative j hat direction. Similar manner, if you go up into the y, increase the value of y, which decreases the value of x, it gets closer and closer to a vector pointing in the negative I hat direction. Not every textbook brings this up. I know that the first semester, or first year I was here, that textbook did. As a side note, the second textbook did not. This textbook does bring this up. So it's one of those things that I think it's good to know, store away in the back of your head, in the back of your mind, and at some point later it becomes probably more useful. far separated. And is that the last thing I wanted to really address here? Did that. Then it gets into some biophysics, and who cares about biophysics, right? All right, I do want to do that special case. Okay. So one more thing, and then we'll put a nail in the coffin of 26 and talk about assessments. So questions before we do a special case of what we've just been doing? I have an electric field, a uniform electric field going to the right. Uniform in the sense that the change in the electric field with respect to whatever direction, we'll call that the x direction, is 0. I have equipotential lines which are perpendicular to it because that's the way they roll. The two lines that I've drawn there, which one will have a higher potential? Which one will have a lower potential? Say it again.
On the right is higher,
And why?
because the electric field goes in the positive direction, which means that one will be closer to.
You said electric field goes in the positive direction. What? Was that to change your mind or move on to someone else?
Okay, so maybe I was looking at it wrong, but we just talked about increasing. No, I don't got it.
All right, anyone else want to pick up where she left off, or?
The one on the left should be larger because it's closer to the source.
Potentially.
If the
Yeah. If this is a positive charge over here creating this, then this would be the higher potential closer to the positive charge. Or if this is being created by a negative charge over here, that electric potential will increase the farther away you get. So either way, we have either positive over there and or negative over here. But this would be the higher potential. So I'll just call it V plus and V minus, or V higher, V lower, however you want to work that. If I want to get a little bit more specific for this, if I have some distance between them, and we'll just call that distance D. I think it's one of the few times I actually use the letter D for distance. Let's figure out what the difference in the potential is. I know that's equal to the negative integral of E dot dr, as we sort of derived earlier. My electric field is uniform, so it is a constant, so that can pop out, so I get negative E dot the integral of dr from some initial position to some final position. So this becomes negative E dot, well, I guess we need to decide which way we're going. Are we going from the positive to the negative or the negative to the positive? So let's go in the direction of the electric field. Going that way. So this becomes R final minus R initial, which is just D. Since I'm going in the direction of the electric field, my dot product is a positive value, so this is just the magnitude of my electric field times D with a little minus sign right there to indicate that we're going to a lower potential. If I go the other direction, my delta V is positive. Because then the electric field and this difference in position are in opposite directions, and therefore this whole thing will be negative, with a minus sign out here, it makes delta V positive. So if I've got an infinite plate here of positive charges, or with an excess positive charges, and another plate over here with excess of negative charges, those are supposed to be parallel, despite the way that I just drew it. My electric field should be relatively constant. Well, if they're infinite plates, my electric field should be uniform in between them. And the value of that electric field, as discussed in some previous lifetime, is equal to the surface charge density divided by epsilon sub naught. Or, for those who prefer the eta over epsilon sub naught.
Sigma's
I'm
so
going to
much
spot
easier
the
to
sigma.
write.
Pardon?
Sigma's so much easier to write.
Yeah.
I don't know why I did eta.
Eta kind of looks too much like an N if I'm doing it in a hurry. The previous textbook used eta, that's why it's there. So if I know the potential difference between these two plates, so let's say that I know that the difference from here to here is 12 volts, or actually negative 12 volts if I'm going from the positive to negative plate. And let me do that in a different color for the typical stunning visual effects. Ooh. Just sort of pops, doesn't it? If this is the case, what is the potential difference between the negative plate and a point halfway in between? So if I'm going from the negative plate to halfway in between the two plates, what is the potential difference? Or what's the voltage? Same question.
Should just be half, so -6 volts.
I understand where you got that from. You made one small mistake.